Hello everyone, welcome back to the channel. In today's topic, we will learn about optimizing the neural networks for a specialized TPU task. So, in today's world of artificial intelligence and deep learning, the quest is faster, more efficient computation will never stop. We will have to see an incredible evolution in how the neural networks are trained from simple CPU to powerful GPU, and how the specialized tensor processing unit or TPU, these chips are designed specifically for the machine learning workloads, have redefined what's possible in a terms of speed, scalability, and cost efficiency. But achieving the peak performance on a TPU isn't automatic. To truly harness their potential, neural network must be optimized for their specialized architecture. That means the fine-tuning everything from the model structure and the data pipeline to the precision format of the memory management. In this video, we will dive into how to optimize neural networks for specialized TPU tasks, understanding the architecture, the bottleneck of the best practices, and the real-world strategies that makes a TPU as a game changer in AI computing. So let's understand what is a TPU. Before we start optimizing, it's a crucial to understand what is a TPU in a different form of the CPU and GPU. TPU isn't like a tensor processing unit. It is customized built in hardware extractor developed by the Google, especially for the tensor operations. The mathematical backbone of a deep learning, unlike a GPU that were initially designed for the graphics rendering and later adapt for AI. TPU were engineered from the ground up for the machine learning workloads. The heart of the TPU is a matrix multiply unit, that is MSXU, which can perform thousands of multiply and add operation in a single clock cycle. That makes the TPU incredible and efficient for the matrix heavy operation. It is found that the neural networks like a convolution and fully connected layer. Each TPU core is also included a high bandwidth memory for the faster data access, a vector processing unit for the element-wise operation, and a massive systematic array that streams data through the chips for the parallel computation. As a result, extreme high throughput and energy efficient, especially for the training and interference of large-scale deep learning models. So the next question, why it is optimization matters on a TPU side. Even through the TPU are the brilliant AI, they don't automatically guarantee to pick the performance for the every model. Many deep learning models, like especially those who develop in GPU architecture, may not efficiently utilize for TPU resources right away. There are many optimization is essential. Data flow benchmarks, model structure efficiency, precision mismatch, and unbalanced workloads. If the data feeding is not match TPU speed, the code stay ideal. Certain architecture may be unutilized for the symbolic array. For the precision mismatch, using these unsupported data types can be wasted and computation cycle. Unbalanced workloads like uh, uneven stand distribution in a multi-core setup to reduce the parallel efficiency. In short, the optimization ensures that the model, data, and hardware work is harmony at minimize the ideal time and maximize the computational efficiency. What is the TPU architecture? We will see the all the TPU architecture in detail format. To optimize effectively, we need to understand how the TPU is structured. Let goes briefly on over the key architectural components like a systematic array, the core computational engine where matrix multiplication happen. It is a 2D grid for processing the element that pass the data like a heartbeat. uh, perform the multiple adds-on operation in parallel. For undefined buffer, it is a speed memory buffer that stores the input, weights, and parallel partial result during the computation. Optimizing the memory access to this buffer is a key for the speed. It is a high bandwidth memory. It stores the large tensor and activation efficient data layout, and rematching reduce the memory back bottleneck. Interconnects in multi-TPU pods. The interconnect link multiple TPU together for a distributed training. Because of the structure, the optimization that can be represented as a large, dense matrix multiplication performed based on the TPU. For the precision optimization, the power of bfloat 16. What is the bfloat 16 like? We can see it in uh, it's like a brain floating point. One of the most important optimization for the TPU is a precision control. While GPU is often used FP32 and FP16, TPU is designed for excel with the bfloat 16. Bfloat 16 maintains the same exponent range of the FP32, but it reduces the mantissa, meaning that it's faster and uses less memory, while still preserving numerical stability for the deep learning task. When you're optimizing your model for the TPU, it converts the computation to the bfloat 16 whenever it is possible. You can use the TensorFlow built-in function like Mixer Precision API to automate the conversion. It monitors and precise loss in sensitive layers like a normalization or softmax. By doing this, you can dramatically reduce the training time without sacrificing the accuracy. For data pipeline optimization, a TPU performance is only the strong as the data pipeline feeding it. If the data loading or processing can't be keep up, even the faster CPU code is it as the ideal. The tips are the optimizing the data pipelines like a user TF the data API efficiently for the pre-batch to overlap data loading with the model execution. For parallelization of data processing, we can use a dot map function to process the multiple samples at once to cache intermediate result. If your dataset fits in on memory, use a cache to avoid the redundant reads. Optimize the data format. Store the dataset in a record format for the sequential reading and better comparison. For distributed data, eventually use a multi-core TPU setup. Make sure your shared gate balance data jump to avoid the bottlenecks as well as optimize the data pipeline that can improve uh, improve at the speed by 30% or more even at TPUs. For the model architecture adjustment, not every neural network architecture plays a nice role with a TPU. Out of the box, some of the models are especially those who customer layer or control flow, they can lead the inefficient hardware usage. Here to make out the model TPU friendly, prefer the dense regular computation. TPU thrives on matrix operation, surpass irregular patterns that reduce the utilization of the TPU. Need to avoid the pattern control flows in a computational graph. We can use TF dot function to ensure the graph compilation. For the batch normalization, replace small batch norms with group norms or layer norm when needed, as a small batch size reduce the TPU efficiency. Reduce the unnecessary reshaping. For excessive reshaping and transposing can be increase the memory access times. Static shape definition that TPU prefer fixed tensor size, dynamic texture dimensions, slow down the XLA compilation. If your model structure align with a TPU strength, larger batch of matrix multiplication, you will notice a massive acceleration in the training optimization. As the TPU continues to evolve, the TPU V5 version 5 and beyond, the optimization landscape is changing too. We can expect a smarter compiler that automatically tune our models, adapt the precision techniques to balance accuracy and performance. Hybrid TPU GPU system that combines the flexibility within the speed, auto shading frame that intelligently distribute larger models across the TPU pods. The goal of the future TPU optimization is to minimal mutual turning and maximum automation, letting developers focus on the model innovation instead of model hardware the conclusion of this video is optimizing the neural network for specialized TPU task is both the art and science. It is about to understand how your model is interact with the underlying hardware and making the right choice in a precision architecture and data flow to unlock that hidden potential. By combining this precision, efficient data pipelines XLA compilation and smart distribution, you can push your neural network to reach unpretended performance level as the field of the AI continues to expand. Mastering the TP optimization will become a key skill for the developer, researchers, and machine learning engineers. It is not just a faster computation, it's about enabling the next generation of the AI breakthrough at scale. So, whether you are training a transformer, deploying a recommended system, or experimenting with generative AI, remember that optimization of TPU isn't an option, it is a key for future proofing of your deep learning success. Thank you very much for watching this video. If you like this video, please like, share, and subscribe. Thank you.